I propose a theory of consciousness beyond spacetime. It explains why light has the same speed in all inertial frames. We can taste thousands of flavors, see millions of colors, smell trillions of odors, and experience countless sounds and bodily feelings. Most theories of consciousness assume that space-time and objects are fundamental. Objects with the right causal or functional properties give rise to consciousness or the illusion of consciousness. There are trillions of specific experiences to explain. It should be straightforward to pick one and explain it. For instance, the taste of mint. Integrated information theory would give a causal account, a Markov matrix. Or Coar would give a Hamiltonian and its collapse. So how many experiences do they explain? 0. Ask each causal or functional theory of consciousness, do you pass the mint test? Some theories propose that consciousness is fundamental. Consciousness creates space-time and its objects. Such theories should answer questions such as, why is the speed of light the same in all inertial frames? Why is there no special inertial frame? Physics assumes this. A theory from consciousness should explain it. It should derive the standard model of physics and go beyond. So, how much of physics do they explain? Nothing so far. We propose that beyond spacetime there is a network of conscious agents. It's like a social network with millions of interacting users. Each agent has the same structure. First, it has a repertoire of possible experiences, or qualia. Given its experience, an agent decides what action to take from its repertoire of actions. The agent then acts on a network of agents. The network in turn alters the experience of the agent. Each agent has a clock that counts its experiences. We model this with Markov chains. The arrows are Markov matrices. A Markov chain with a clock is called an enhanced chain. I will focus on the dynamics of experiences in the enhanced chain. Consider a simple agent that has only 4 experiences: red, green, blue, and orange, one at a time. It experiences these colors one at a time in some random sequence. We can describe this with a Markov matrix. For instance, its second row of numbers means if I see green now, then with probability 0.5, I will see red next, and so on. Now suppose that we only attend to red and green. The matrix on 4 colors induces a dynamics of red and green. We can describe it by a smaller matrix, whose entries are determined by the larger matrix. The smaller matrix is called a trace of the larger. For completeness, I give the formula for computing the trace matrix. For those interested in active inference, the trace chain minimizes surprise. No probabilistic model does better. Tracing induces a partial order on Markov chains. Matrix M entails matrix N if M is a trace of N. We write M less than or equal to N. Markov chains form a non-Boolean logic under the trace order, including meets and joins. 2 Markov chains may join to form a larger chain. This is key for active inference and artificial intelligence. For any Markov chain P, the traces of P form a Boolean sublogic of the trace logic. If P has n states, its Boolean sublogic has 2 to the n members, including P and the empty set. Relativistic spacetime can be constructed from the trace logic. I will now show how. Consider again an agent that can see 4 colors, and consider its trace onto red and green. On the left, a counter increments when any color appears. On the right, a counter increments only when red or green appears. The counter on the right is slower. It sees fewer colors. This is time dilation. Time runs slower on a trace. So gaps between ticks are longer on a trace. Let delta t0 be the gap between ticks of the big chain, and let delta t be the gap between ticks of the trace chain. Then we can write delta t equals gamma delta t0, where gamma is greater than or equal to 1. The trace also creates length contraction. The distance between states shrinks in a trace. This distance is determined by something called the commute time between states. Commute time is the expected commute time between 2 states, A and B, is the expected number of steps from A to B and back. For instance, the commute time between red and green in this Markov chain is the expected number of steps from red to green and back to red. The first thing to note is that there are an infinite number of paths to consider. Red might go to green, then back to red for a commute time of 2. Or red might go to green, then to blue, then to green, then back to red for a commute time of 4. Or red might go to itself first a few times before going on to other colors. So we see that the commute time requires an infinite number of paths to compute. Remarkably, there is a way to embed the n states of a Markov chain in an n-dimensional Euclidean space, such that the squared distance between states is the commute time. Trace shrinks distance. In this matrix, the commute time between red and green is 5.7. So their distance is the square root of 5.7, which is 2.4. Now we look at the trace chain on red and green. We find that the commute time is 3.5, so their distance is 1.9. We see that taking a trace shrinks the distance between states. We find that lengths contract on a trace. If L0 is the distance between 2 states in the original chain, and L is their distance in a trace chain, then we have L equals L0 divided by gamma prime, where gamma prime is at least 1. When we take a trace, time dilates by a factor of gamma, with gamma at least 1. Length contracts by a factor of gamma prime, with gamma prime at least 1. When does gamma equal gamma prime? For most Markov matrices, they are not equal. But for 2 classes of Markov matrices, they are equal. The first is the cyclic matrices. The state goes from 1 to 2 to 3, all the way to n, and back to 1 in an endless cycle. We use them to build Minkowski space. The second is the uniform matrices, namely n by n matrices whose entries are 1 over n. For generically chosen Markov matrices, gamma prime does not equal gamma. These matrices will give rise to curved spacetimes. For now, we will focus on n cycles. We have seen that the trace operation induces time dilation and spatial contraction. We therefore propose that each trace chain corresponds to an inertial frame. Therefore, moving from one chain to another via the trace operation corresponds to a relativistic boost. And for n cycles, gamma is the Lorentz factor. Consider a 3-cycle on red, green, and blue. The commute time between any pair of states is 3. So the distance is the square root of 3. This is our inertial frame. So its Lorentz factor, gamma, is 1, and its velocity, v, is 0. Now trace onto 2 states, red and green, or green and blue, or blue and red. These are 2 cycles. For each 3 ticks of the 3 cycle, we only get 2 ticks of a 2 cycle. So gamma is 3 divided by 2, or 1.5. The velocity v is now about 3/4 the speed of light. Finally, we trace onto the single states red, green, and blue. These are 1 cycles. For every 3 ticks of the 3 cycle, we only get 1 tick of a 1 cycle. Therefore, gamma is 3, and the velocity, v, is now about 94% of the speed of light. There is no biggest Markov matrix, and thus no top matrix of the trace logic. This entails that there is no preferred inertial frame. A key feature of spacetime is the relativity of simultaneity. Whether 2 spatially separated events occur at the same time depends on the observer's reference frame. We now show how this arises from the theory of conscious agents. Consider this graphic representation of a Markov chain. The matrix representation is harder to understand, so we will stick with the graphic representation. Let's start off in state 0 in the middle. With probability 1/2, we go to state 5, or to state 1. Suppose we go to state 5. Then we cycle through the states 5, 8, 7, 6, 5, and so on. The commute time between any pair of states is 4. Now suppose instead that from state 0 we go to state 1. Then we cycle through the states 1, 2, 3, 4, 1, and so on. Once again, the commute time is 4 between any pair of states. Now suppose that we choose a boosted inertial frame, obtained by tracing this matrix on all of its states except state 6. It turns out that the traced matrix looks like this. Now the commute time on the left is 3 instead of 4, but the commute time on the right is 4. Now suppose that we choose a boosted inertial frame obtained by tracing this matrix in all of its states except state 2. It turns out that this traced matrix looks like this. Now the commute time on the right is 3, but the commute time on the left is 4. This is the relativity of simultaneity. A trace can change the rate and order of events. We can define the instantaneous speed of a state of a Markov chain to be the expected number of new states in one step. So in this simple Markov chain, state 1 has a probability of 0.99 of staying in state 1, and a probability of 0.01 of moving to state 2. So its instantaneous speed is 0.01. For state 2, the probability is 1 of moving to state 1. So its instantaneous speed is 1. Instantaneous speeds vary from 0, which is the slowest, to 1, which is the fastest. We therefore identify light as a projection of Markov chains whose states all have the fastest instantaneous speed. These are the n cycles. The trace of an n cycle on a subset of m states is an m cycle. Thus, the trace of light is light. The trace has the same instantaneous speed as the original. This is the reason that the speed of light is the same in all inertial frames. Light is the projection of n cycles. What property of n cycles projects to the polarization of light? First, note that there are n-1 factorial distinct cycles of length n. We can define a natural circularity parameter on these cycles that varies from -1 to 1. I display this technical definition for completeness, but in the interest of time, we'll just discuss it intuitively. The circularity parameter is +1 for the counterclockwise n cycle and -1 for the clockwise n cycle. These correspond to circular polarizations of light with helicities +1 and -1. Here's an example of a 14 cycle with circularity parameter 0.5. This is an example of elliptical polarization. The precise sequence of states is this. Here is an example of a 14 cycle with a circularity parameter mu equal to 0. This is an example of linear polarization with this precise sequence of states. So how do we embed this model of light into spacetime so that every pair of states is equidistant? This is impossible in general for Euclidean 3 space, but with Minkowski spacetime, we can embed it sequentially in time, as illustrated here. We have identified trace chains as inertial frames, and the tracing process as a boost. This means that an acceleration is a sequence of chains of traces that differ each by one state. So an acceleration is the projection into spacetime of a path through the trace logic. What about mass? How does it arise from Markov dynamics? We propose that mass is entropy rate. A cyclic matrix has 0 entropy rate. A matrix with many links has a high entropy rate. Here is the definition of entropy rate. Sum the entropy of each row, weighted by the stationary measure. Entropy rate is central to information theory and its concepts of channels, coding, capacity, and distortion. If spacetime is a headset, perhaps black holes appear when the channel capacity of the headset is exceeded. Light is massless, so its entropy is 0. Only cyclic matrices have 0 entropy rate. So we propose that cyclic matrices project to light. Any matrix with an entropy rate greater than 0 cannot be cyclic. For this reason, no object with mass can reach the speed of light. Here is a simple example of a massive particle. State 1 goes to state 2 with probability E rather than with probability 1. This makes the entropy rate of the matrix, and thus the corresponding mass, greater than 0. We have given the class of matrices that correspond to photons. Now we must give specific classes of matrices that correspond to the specific massive particles of the standard model of physics, namely to the specific leptons, quarks, and massive bosons. I will now look briefly at the asymptotic behavior of Markov chains. of enhanced Markov chains. We have seen how the trace logic of Markov chains connects them to relativistic spacetime. We will now see how the asymptotic behavior of enhanced Markov chains connects them to quantum theory. The state space of a Markov chain often looks like this. The red region corresponds to transient states of the chain. Each disk corresponds to an absorbing set of states. Each absorbing set acts like a roach motel. Once you get in, you don't get out. Each absorbing set is carved into subsets, like pieces of a pie. These are called asymptotic sets. Suppose we start the chain at the state indicated by the red dot. Then the state of the chain will wander around in the transient states until it hits an absorbing set. Once it hits an absorbing set, it's stuck inside. It stays inside that absorbing set. And at each step of the chain, it goes to the next asymptotic state in a never-ending cycle. This asymptotic behavior of an enhanced Markov chain P is described by the harmonic functions of P. These are eigenfunctions with eigenvalue 1. These harmonic functions can be written in the form g sub rho k as indicated in this equation. The harmonic functions of enhanced Markov chains are identical in form to the wave functions of quantum mechanics, of free particles. This allows us to make physical interpretations of the asymptotic behavior of enhanced Markov chains. Suppose, for instance, that the Markov chain is in absorbing set 1, which has 4 asymptotic sets. Then the Markov chain for this absorbing set is a 4-cycle. It has 4 harmonic functions which correspond to the quantum wave functions for free particles. The first has momentum h over 4, where h is Planck's constant. It has an energy of hc over 4. Similarly, one can compute the momenta and energies corresponding to the other 3 harmonic functions. So, conscious agents and the trace logic give us a non-local hidden variables theory of quantum phenomena. This theory is measurement dependent, since each trace is a different way of observing. Markov matrices are the hidden variables. Their asymptotic behaviors are perceived as quantum phenomena. The trace logic on Markov chains gives us the Lorentz transformations of spacetime. The harmonic functions of enhanced Markov chains give us quantum wave functions. Together, they create a new approach to relativistic quantum theory. For instance, we can start with an enhanced Markov chain on 3 states, red, green, and blue, and compute its wave functions, the harmonic functions. Then we can take its trace on all pairs of states, and for each pair compute the new wave functions. Then we can take its trace on all the single states, and for each one compute the new wave functions. This means we can combine relativity and wave functions without requiring quantum fields defined over spacetime. Although quantum field theory has been a powerful tool for nearly a century, it has some well-known serious problems. Most notably, it gives a wrong prediction for the mass energy density of the vacuum. It's not wrong by 1%, or 10%, or 100%. It's wrong by a factor of 10 to the 120th power. The problem seems to arise because sums over paths in spacetime diverge. But sums over paths in Markov chains do not diverge because probabilities must sum to 1. We have discussed how the Markovian dynamics of conscious agents can appear as the mass, energy, and momentum of particles. What about particle spin? We propose that spin is a projection of the determinant of the Markov chain. Consider again this Markov chain. Its determinant is 0. Its mass is positive. Now suppose that we choose a boosted inertial frame obtained by tracing this matrix in all of its states, except state 0. Then we obtain these two Markov chains. The chain on the left has determinant 1, whereas the chain on the right has determinant -1. Both have a mass of 0. The initial chain with determinant 0 and positive mass is similar to the neutral pion, which has spin 0 and positive mass. The pion decays into two photons with helicities +1 and -1. This matches the two chains we obtain in the trace. Classical bits can be cloned at will. Quantum states cannot. The reason is that quantum operators are linear. Unitarity is not needed to prove this no-cloning theorem. Similarly, Markov matrices are linear operators. They cannot clone probability measures, which are Markov states. Thus, Markov states, like quantum states, are private. If you want privacy of states to model privacy of qualia, then Markov states do the job. If I want to learn the trace on red and green, I can sample the sequence of reds and greens as they occur. If I want to know the determinant or asymptotics of this trace, I need a long sample so I can estimate the whole matrix and compute its determinant or asymptotics. If I want to know the current state of the trace, I need only a sample of one trace. We face a fundamental limit. Estimating asymptotics of a matrix precludes knowing the state accuracy. Knowing the state accuracy precludes knowing the asymptotics of the Markov matrix. This is the origin of the Heisenberg uncertainty principle. The join of two Markov matrices is a new matrix that entangles the two. The join does not just entangle one property, such as the determinant, but all properties encoded in a matrix. This is the origin of entanglement and steering in quantum mechanics. What is next for the theory of conscious agents? We need to find the Markov matrices for each elementary particle of the standard model. We already have the matrices for the photon. Then we need to explain the amplitudes for particle scattering and particle interactions. We need to show how curved spacetime emerges from the trace logic. And we need to show how the trace logic provides a new foundation for theories of active inference. In summary, we propose a theory beyond spacetime. What spacetime assumes, our theory explains, including why the speed of light is the same in all inertial frames and why there is no preferred inertial frame. Spacetime is just a headset. We offer a Markov theory of consciousness beyond spacetime. It allows us to reverse engineer that headset. Brains do not create consciousness. Brains are just icons in our headset. They are the headset's way of representing how the headset is engineered. Many thanks to my collaborators, and especially to Chetan Prakash and Shwapon Chattopadhyay.